So some sort of tensor conjunction. Yeah, so this is the usual tensor homojunction in reverse direction, right? And now we have a function from V tensor V to N, but this is can be made into a function from V to N by just applying hom blank N to the co-multiplication of V, yeah? So there's a co-multiplication on V. V goes to V tensor V over A. And if you apply hom blank N to it, you will get a map in the reverse direction. And so all in all, you get a map from L to hom Vn, which is alinear. And this is actually what we define as the composition of these two maps, F and G. Okay. Yes. And the identity, I didn't write on the board. I will mention it later on. The identity morphism, they are given by the co-unit. So yeah. So an identity would be a homomorphism inside the homomorphism space from M to M, right? So we have to find a map from hom to hom V comma M. And we get this from a map from hom M, hom AM by just applying the co-unit. Okay. So that's this Kleisli category, this kind of a bit strange looking category, but yeah, it's somehow built in such a way that it describes a morphism space between induced modules. Okay. Now there's another, well, another description. So this Kleisli category is somehow quite conceptual, quite categorical, and so on. But there's actually another description of this Kleisli category, which goes as follows. One uses this description that we before, so the homomorphism spaces between M and N, given by this homomorphism space from M to hom V comma N. And if one uses the bimodule adjunction, then this can be also described as homomorphisms from over A tensor A op from the co-ring V to hom Mn. And then you can describe how composition works and so on. Okay, that's, yeah, doesn't sound like much. But in fact, this is quite useful a description. Namely, we can use that V has a projective cover. So V is an extension of V bar and A. Yeah, so we can cook up a projective cover of V by taking a projective cover of V bar and a projective cover of A. A projective cover of V bar is given by V bar because V bar is a projective bimodule. That was one of our assumptions, or equivalent to one of our assumptions. And A, the diagonal bimodule, has this projective cover, this space, A tensor L tensor A. If you want, that's one way to write the projective cover of this space. Okay, so this means that you can write this thing here as a subspace of this of morphisms from this space. So this homomorphisms from V to hom Mn can be written also as a subspace of this projective cover, A tensor L tensor A plus V bar to hom Mn. But now again, we have some sort of induced module here. So A tensor L tensor A is some induced module, and V bar is a projective bimodule. So we discussed last time that this means that V bar is also of the form A tensor phi tensor A for some LL bimodule phi. And so this space here can also be written as LL bilinear maps from L plus phi to hom Mn. Where phi is a generating set for V bar, so to say, and L is just this product of fields that you have. Okay, and then you can, see again what kind of space is it, and what are morphisms here? So these are tuples of maps, Fi representing the maps from L to Hom Mn, and Fi representing the maps from phi to Hom Mn. And they have to be arranged in such a way that Fi minus Fja plus F evaluated on d0 of A is equal to 0. So what does F evaluated at d0 of A mean? So d0 of A will be some element of V bar. And V bar now is some sort of, some element. V bar is isomorphic to A tensor phi tensor A. And so you can just take the corresponding, A's and F's, Fi's and so on, and F-phi's. Okay. Yes. So let's see an example what this actually means in practice, how we can use this. And composition law is described in terms of D1 of D1, this map from V bar to V bar tensor V bar. Let's see an example. Okay, so the example is the following algebra. So it's the path algebra of A2 tilde with one relation, the relation alpha gamma, which makes this path algebra quasi-hereditary algebra. And in this case, one can check that, for example, Teresa Conde's criterion is satisfied, so the algebra R will be basic. And the subalgebra R is the subalgebra given by only alpha and beta. And the V bar will be the projective bimodule generated by this E3 tensor over K with E1. So somehow the projective bimodule corresponds to this arrow gamma from 3 to 1. You can think about it like this. Okay. So what is a morphism? I said a morphism is given by one map Fi from Mi to Ni, as usual, somehow for quiver representation. And then you have this maps Fi corresponding to the generators of your projective bimodule. So in this case, you have only one generator, Fi, going from M1 to N, going from 1 to 3, so to say. So you have to put a map Fi, which goes from the space M1 to the space N3. Okay. And now I say this is a morphism of quiver representation. So you have this quiver representation of A, right? So A is just the path algebra of this usual A3 quiver. So it's just this tuple of vector spaces, M1, M2, M3, together with these linear maps, M alpha and M beta, and same for N. And now what is a representation from M to N? It's this, as usual, as quiver representations are normally. So it's a map Fi for each vertex. So F1 from M1 to N1, F2 from M2 to N2, and M3 from M3 to N3. And then there's this additional diagonal morphism, F5 from M1 to N3. So this is the data of this. And now there's a commutation rule. This commutation rule is this one, right? So AFI minus FJA plus FD0 of A is equal to 0. So in the usual quiver representation world, this correction term here does not appear. So it's just commutation relation. AFI minus FJA is equal to 0. That's the rule we're all familiar with, right? Okay, but it can be slightly twisted by this term D0 of A, right? Okay, here in this example, actually, the example is chosen in such a way that the D0 is equal to 0. So what are the commutation relations this morphism should satisfy? The commutation relations are just that the small squares both commute. And there's no condition on F5. It's just an arbitrary other morphism that you're also allowed to do. So for example, if you take the simple representation at 1, K0, 0, and the simple representation at 3, 0, 0, K, you will see that you get a morphism from the simple at 1 to the simple at 3. which couldn't happen in the Boolean case, of course, because you're dealing with simple modules and Schur's lemma holds. But in the exact case, it can happen. Right? It can happen that you have two simple objects of an exact category, and they have morphisms between each other. If you translate this back to induced modules, really for this algebra, you get you can see this actually what happens here. But let me mention one further fact, right, which is in some sense a bit special. I think you need an additional condition, or I'm sure you need an additional condition for this. So what is an isomorphism in this category? An isomorphism is one where all the horizontal arrows are isomorphisms. There's no condition on the diagonal morphisms except for the commutation relations. Okay. So let's translate back. And here we see the Auslander and Reiten of F delta.
Can I interrupt?
Yes.
Can you say something about composition?
Yes. Yes. In this example or in general?
No, in this example. In this example.
In this example, yes. So if you had two of these next to each other, so you had some sort of, maybe I can try to annotate this in some way. So if you had some sort of, I hope this is visible, L1, L2, L3, and then you had this so like this, and then you have another web here, G, should be dashed, but okay. So G phi, G1, G2, and G3. Okay, so then in the composition, G composed with, F composed with G. On the horizontal things, it all looks as we are used to. So G composed with F composed with G at I is just Fi composed with Gi. And now the question is, what is on the diagonal map, right? So F composed with G at phi. In this case, it will just be F phi after G1 plus F3 after G phi. And in general, there will be some term, again, somehow, F, like this term is number 4. So maybe let me use another color. Blue. There will be an additional term, Fg, evaluated at D1 of phi. So D1 of phi is some element of V bar tensor V bar, and then you can somehow apply F on the first component and G on the second component, so to say.
Okay, thank you.
Does that answer your question?
Yes, thank you.
Yeah. Okay. Great. So let me continue. Oh, now I have to erase the annotation. Yes, okay. Yeah. So yeah, now I went back. So in this example, it's the case that all the indecomposable A modules stay indecomposable if you regard them as modules of the Kleisler, objects of the Kleisler category. And so you have 6 indecomposables because you have 6 indecomposables for the path algebra of A3 from 1 to 2 to 3. And so you see here this nice Auslander and Reiten quiver of A3. But there's this additional morphism, additional irreducible morphism from the simple at 1 to the simple at 3. So the simple at 3, if you induce it, corresponds to the module 3.1, which is the standard module at 3, right? So in the bottom here, you have the standard modules for 1, 2, and 3. The standard modules for 1 and 2 are simple, and the standard module for 3 is not simple. It gives you this additional morphism from 1 to 3.1, right? Which corresponds to this diagonal yes, diagonal morphism. Okay. Now I said that in this example, it's a bit special and maybe a bit misleading because in this example, indecomposable objects of the modular category of A stay indecomposable in the Kleisli category of A, V. This is in general not the case. It's usually far from the case. Usually the Borel, so this algebra A, is much more complicated than the category of objects in the Kleisli category. So yes. So let me just give one example that I computed a while back with Agnieszka Bocenta. It's about decomposing indecomposables. So in general, as I said, the indecomposable A modules can decompose in the Kleisli category because you have further morphisms that you can use to split things. Okay. So let's take the following example. It's the bound path algebra given by this quiver and this set of three relations. So going from 3 to 1 to 3 is 0, going from 2 to 1 to 2 is 0, and going from 3 to 1 to 2 to 1 to 3 is 0. Okay. That might look strange, but it's, in fact, a nice counterexample in the world of quasi-hereditary algebras, I was told by experts in the field. I think, after we computed a while with this kind of examples, we found also this example in a paper by Walter Mazurczuk, for example. It belongs to one class of algebras that we saw already, which is the Ringel duals of dual extension algebras of path algebras of trees. So it's the Ringel dual of the dual extension of A3, in fact. Okay. Again, R is basic, one can check. And B is of type A2 tilde. So it's of tame representation type. It's the subalgebra given by gamma, by beta, and by delta beta. So there's an arrow from 1 to 2, an arrow from 2 to 3, and an arrow from 1 to 3. Okay. And now we can look at, again, representations. So you have this B is what I called A before. So please replace B by A here. Okay, so we all know the representation theory of A2 tilde. There's a one parameter family of representations. So this 1, 1, and then the lambda here. Some scalar. So this is a one parameter family of non-isomorphic indecomposable representations. And in fact, it turns out that this whole one parameter family collapses. That this whole one parameter family becomes isomorphic in the Kleisli category. And why is that? That's because you have this additional freedom. So here, in this case, D0 is not 0. D0 of this arrow from 1 to 3 is actually this arrow, this going first, this diagonal arrow here, where the lambda is, and then the arrow from 2 to 3. Right? So therefore, the commutation relation for the arrow from 1 to 2 is the usual one, right? So the square should commute. And the commutation relation for the second square, the lower square, is also the usual one. The square should commute. But the commutation relation for this arrow labeled by lambda from 1 to 3 is not the usual one. It's not going first this arrow and then this horizontal map is equal to this arrow and then the horizontal map. It's actually this composition here going first down then right minus the composition going first right then down is equal to going first the diagonal and then this one. Yeah, and you can see that this is an isomorphism because all the horizontal things are isomorphisms. Okay. Yes. So that's what's happening. So you get some sort of quiver representation like description, but it's a bit more complicated to work with because you have this additional diagonal morphisms. But some things are still nice, right? So isomorphisms are still the ones where these horizontal maps are all isomorphisms, for example. Okay. Now we want to understand this category as an exact category, so we better understand ext actually here as well. And yeah, there's actually many ways to describe ext in the space. And yeah, here are some of them listed. And yeah, let me comment a bit about them. So we had this description of the Kleiner category. Homomorphisms were homs from M to hom A Vn. And actually this holds also for X, basically because V is a projective. No, V is not projective. V is projective on either side. Yeah, that's the key part here. One space that you can use to describe extensions is X1 from M to hom A V, N. And then we had another description where we could be looking at AA bimodal homomorphisms from the co-ring. And there you have X1 from V to hom Mn. The other one is, of course, ext in the ambient category mod R between the induced modules. And the last one is the space of Unida extensions between R tensor M and R tensor N, because this is an exact category. You can make sense of what are Unida extensions. Yeah, this all these spaces are isomorphic. Okay. Yes. So I won't give the proof of this lemma. I think the main parts of this lemma are due to Ovsienko. Some unpublished notes. But I will try to give you some flavor of how it is to work with this category and to prove this. So one part of the lemma that one has to prove is, for example, that to describe split extensions in this Kleiner category. Right? So let's try to do this. And I wanted to do this because it highlights also a bit about how the proofs work in the statements I gave the day before yesterday. Yeah? So one important tool in the works here in the proofs is this sequence, right? So you have the co-unit epsilon from V to A, and the kernel is this projective bimodule V bar. And now you can prove a lot of things by just applying this functor to this. And if you do this, you get somehow extension, you start with homomorphisms, A-module homomorphisms from M to N, and then you get to homomorphisms in the Kleiner category from M to N, and then you get this space hom by some tensor homojunction from V bar tensor M to N. Then you go with X1 from M to N over A, and then you get X1 between the induced modules. So this is what you get when you apply this, and you use some identifications. Okay. So now what we want to show is that the image of the connecting morphism here from this hom space to this X1 space coincides with the sequences which are split in the Kleiner category. So sequences of A modules. Okay. So the upper row here is just applying blank tensor M to this important exact sequence V bar to V to A. Get this. Now, what is this connecting morphism? The connecting morphism here just takes the push out of the morphism here along a map from V bar tensor M to N. Okay, so then you get a map of A modules N to E to M. Okay. And now I claim that such a map that you can obtain as such a push out sequence, such a sequence is always split in the Kleiner category. Why is that? Because any A-linear map via the co-unit can be regarded as a map in the Kleisli category. So this map P from E to M is in particular a morphism in the Kleisli category. But also you have this little morphism S from V tensor M to E. And via tensor homojunction, this can also be regarded as a morphism in the Kleisli category. But now you can look what happens if you compose P and S. If you compose P and S, because this diagram here commutes, you get epsilon tensor M here. But epsilon tensor M is actually corresponds to the identity morphism in the Kleisli category. So this means that the map P here splits as a map in the Kleisli category. Okay. Using this S. And this also works conversely. So if you have a splitting S of this map P in the Kleisli category, then this will give you such a commutative diagram here on the right, such a commutative square on the right hand side. And then you can take the kernels of this map here, take kernels, and then you get a map from V tensor M, V bar tensor M to N, which induces this sequence as a push out. Okay, so that's some nice machinery. It tells you about the interplay between A modular homomorphisms and viewing morphisms in the Kleisli category and so on. That's somehow behind many of the proofs, and also this long exact sequence here that you obtain is crucial in a lot of proofs that we do. Okay. Yes. Let me finish off this part by saying now you can also describe the exact structure intrinsically in terms of the Kleisli category in some way. So you have this these maps in the Kleisli category, which you can describe as this tuples Fi, Fi, I running through the vertices of the quiver, and phi running through these diagonal arrows, these generators of the projective bimodule V bar. And then a sequence like this is actually a conflation if and only if you just look at the maps Fi and Gi, you actually obtain let's say a sequence of vector spaces, and this should be an exact sequence always. And furthermore, you want that the composition of this G and this F is 0, which need not be the case even if these are all exact sequences, because these diagonal arrows might mess up things. So these are the conflations written in the Kleisli category intrinsically, rather than going to the ambient category of mod R, right? Which would be another way of describing this. And then you can also describe the inflations and the deflations. So inflations are just the things where the Fi are monomorphisms, and the deflations are the ones where the G or the Gi are epimorphisms. Okay, so that's nice, and somehow you can really work, in some sense, work with this as a category of quiver representations, although it's a bit complicated. Okay. Yes. Now this is for some sort of excursion to homomorphisms and extensions in the Kleisli category. But now, how does this help? How do these methods give you something for uniqueness? So how do we prove uniqueness actually? And for this, we have to go back to the A-infinity machinery, of course, because that's how we prove things. And actually, we have to do A-infinity not in the category of vector spaces, or the category of graded vector spaces, but we actually have to do A-infinity in the category of bimodules. So what do we have? So just for this talk, I called this an A-infinity co-ring, which somehow is consistent with the literature, but I think this object has not appeared anywhere else. At least I didn't see it before. So it's what you think it is, right? It's some sort of A-infinity coalgebra object in the category of AA bimodules. So you have these A bilinear maps, mu n, of degree 2 minus n, which go from, if we call this f just for now, which go from f to the tensor n. And these maps should satisfy some co-A-infinity relation, which is given by this equation here. So it's just a dual object of this A-infinity algebra, but now regarded as in the category of bimodules. Okay, great. And now, what I want to recall again is you had this Kardashvili's theorem, which tells you if you have an A-infinity algebra, you can take homology and you get another A-infinity algebra. In some sense, we want to go reverse, right? Transfer something to some quasi-isomorphic complex, but now we are not working over a field, so we can't use these splitting arguments that were, for example, behind Merkulov's construction. So we have to do something else, and the something else we can just assume that the components of this thing are projective. So for example, you can take this co-ring, you can take a projective bimodular resolution of this co-ring, and then one can prove that this bimodular resolution has actually the structure of an A-infinity co-ring, with the differential just being the differential of the complex P. Okay. We were actually not the first one to observe this or similar results. This is certainly, or most likely this is not the complete list, but at least we were able to track down the following references. So Jesse Burke has a paper where he describes an analog of this statement for the case where A is a commutative ring. And I'm not quite sure whether he uses rings or co-rings here, but yeah. So he has this passage to the projective resolutions. And Chris Negron, Yuri Volkov, and Sarah Witherspoon, they have a paper where they do this in the special case where A is just A regarded as an A co-ring, and P is some projective resolution of A. Okay, and they use this, I think, for doing some sort of support variety theory or something like that, if I remember correctly. Okay. Yes, so you can translate the structure transport of co-ring structures to projective resolutions at the expense of using having this only not on the nose, right? Co-multiplication, not a co-associative on the nose, but up to homotopy and up to a system of higher homotopies, so that you get an A-infinity co-ring structure. Okay, so that's what we actually do. And we do this for a projective resolution that we are given quite naturally. So again, we use this exact sequence. V bar includes into V with the projection being the co-unit to A. And now we use the classical horseshoe lemma. So V bar is a projective bimodule. So it has a one-step projective resolution consisting just of V bar, concentrated in degree 0. And the algebra A as a bimodule has, for example, the bimodule bar resolution, or the reduced bimodule bar resolution. Okay, and so if you sum these two resolutions together, you can obtain a projective resolution of your co-ring V. Right. Yes. And now we want to use this explicit bimodule bar resolution to explicitly describe this A-infinity co-ring structure in terms of the differential on these corresponding semi-free ring TA of V bar. So how do we do this? First of all, so what's the resolution? So we just sum them together, and then you have this mu1 in degree 1 and mu1 in degree 2. And if you go through the proof of the horseshoe lemma, you see that actually you can choose mu1 of 1 tensor x tensor 1, where x is in the radical, to be omega hat, which is some sort of generator of this L, right? Omega hat x minus x omega hat minus d0 of x. So d0 of x is actually an element of v bar, so this definition makes sense. And you can use as I said, you can use the proof of the horseshoe lemma and explicit calculation to see that this is a possible definition in the of this mu1. Okay. Now the next steps after we have analyzed mu1, right? You want to understand also mu2, mu3, and so on, right? So mu is next somehow, mu2. How do you define mu2? The second higher multiplication, higher co-multiplication. So you have the mu, which is the co-multiplication on the co-ring V. So that's a map from V to V tensor V. And now V has this explicit projective resolution, and V tensor V also has the tensor product of this projective resolution with itself. There was no space on the here, so to put the term here, right? It's already too complicated for the slides if you don't want to decrease the font size too much. But it's just the tensor product of this term with this term in both directions. Okay. And now we want to choose a lifting of this mu to some map here. And actually, we can prove that the following is a lifting. So mu2 of phi, where phi is one of the elements of V bar, is just phi tensored with omega hat plus omega hat phi plus d1 of phi, where d1 is actually this map from V bar to V bar tensor V bar. So it's an element of V bar tensored with itself, which is an element of, which is one of the summons of this thing. Okay, and then we checked also explicitly that mu2 you can describe by this formula. This maybe looks a bit scary, but yeah, all the ingredients are still just the things that we have at our disposal. We have somehow the omega hat, the generator, and we have the maps d0 and d1. Right? So here we use d0, and you use Sweetler notation. So writing d0 of x as some sort of sum of x1s, x2s, and x3s. So d0 of x is an element of V bar. So V bar is isomorphic to A tensor phi tensor A. So we can write it like this. And then we pick out the summons which makes sense in this tensor product of A tensor J tensor A with A tensor L tensor A plus V bar. So it will be these two terms. Okay. So you can hopefully imagine this works. I think it takes a few pages to really check that these are possible lifts here. And actually we do it for all degrees in this case, in the case of mu2. And now, you have mu2. Now we can go on. We can go on with mu3 doing the similar method. So what about the higher multiplications? Mu3 is of degree -1. So actually, it will be given by such maps, right? Mu3 0, Mu3 1, and so on in these degrees. And what it is it's a lifting of the zero map, actually. That's how we set out things. And it's this lifting of the zero map. We know the differential here on the tensor complex. And this is set up in such a way that it satisfies the A-infinity relations for this A-infinity co-ring. And one can check again, it's this formula. This takes a few more pages. but you can ask, okay, you know, 2 mu2, that's maybe 5 pages, and then 15 pages for mu3. How long did you actually go? What did you do? And actually, the way our proof works is that we have to compute until mu6 0. So we do all these calculations, similar methods. It takes now a bit more than 100 pages, unfortunately. Why that far somehow? How did we know that we would have to calculate until then and then stop somehow? If you look at mu50, some generator phi of v bar, you see the term 1 tensor phi 1, tensor phi 2, tensor phi 3, tensor phi 4, tensor phi 5, tensor 1, which is actually something that arises, if you do d1 of phi, d1 of phi is some element of v bar tensor v bar, so it's some element of a tensor phi tensor a tensor phi tensor a, if you wish, if you identify this with this isomorphic module. And it can happen that all the a components lie actually in the radical of a, and you can get such a term here. And this term will actually give a non-trivial contribution to the higher multiplications. So this is at least how far we have to compute, at least until mu5. And then we actually have computed one further, because then we can set up an induction argument to say, okay, from term mu6 0, there will be no further contributions to the terms, right, of the infinity structure that we're actually interested in, namely the infinity structure on this X algebra. So we have to go one step further than the mu50, namely to the mu60, and for the terms 1, we have to go a bit lower. We don't have to compute mu61 because there are less contributions here. Okay. Yes, so that's somehow the longest part of the calculations. It's not really the most difficult one in some sense, because it's just an explicit calculation. Okay. And even if the calculations would be slightly wrong, it wouldn't somehow hopefully matter that much, right? If there was a slight calculation error, because all that we care about somehow in many of the terms is just that they lie in the correct degree, so that they don't contribute any higher multiplication term to this infinity algebra you're actually interested in. Okay. Yeah, so what we do is we take this infinity covering structure on P star in the next step, right? And we dualize by applying HOM into HOM LL to get some A infinity structure. It's just some sort of duality. And this A infinity structure turns out to be A infinity isomorphic to the X algebra we're actually interested in. Okay. Now, how does that help? So that's one key part of the strategy for uniqueness, which I just want to recall briefly before going to the last part. So now going to this question, how to go on. So what is the strategy for uniqueness now? The strategy is, as I said, the steps that we had. We compute explicitly the covering structure on the projective resolution of the covering, V. Then we dualize to obtain the explicit description of the A infinity structure on this X algebra in terms of D0 and D1. Okay. Now, if you do this twice, right, for two different presentations of V, different D0, different D1, potentially, then you get two different A infinity structures on this X algebra. But by Khatishvili's theorem, there's only one up to A infinity isomorphism. Okay. Now there's only one, so they're isomorphic. Now, applying A infinity causal duality to these explicit structures, by the way we set up things, is actually inverse. So if you apply A infinity causal duality to these explicit A infinity structures, you get back the presentations you started with on the nose. And then there's one little step, which is, of course, important. A-infinity causal duality is functorial. So in particular, if you take A-infinity isomorphic structures, which by Kadishvili we have, we get isomorphic ring extensions. Yeah, that's how things work. And that's how we prove uniqueness in this tuple A, R. Yeah. Okay. Maybe not the easiest strategy to come up with, but one that at least works. Okay. That's how much I want to say about proving uniqueness of the ring extension A, R for the exact category of, yeah, as I should mention again, this uniqueness. In our calculation, we want to simplify things, so we only proved it under the assumption of directedness of the co-ring V, so only in the case that we are dealing with the category F delta for a quasi-hereditary algebra. So there's nothing done yet even for standardly stratified anything more general. Okay. So how to go further? How to go more general? And I want to conclude the talk with just gives you some sort of ideas what you could work on if you want to. Yes, so let me recall what I started with. And yeah, one of the things I wanted to say, I claimed maybe that's a good thing, what should be a equivalent relations for an exact category. One thing one would like is then a description of the exact categories which are equivalent to such things. Right? Analogously to this theorem that an abelian category is equivalent to mod A if it's Hom finite, has enough projective, and it's a length category. Okay, so now you can think what is easy, what is difficult for exact categories in this setup. Of course, K-linear and Hom finite are conditions just on the category, so they make also sense for exact categories, and I believe they should be unchanged. Enough projectives also makes sense for an exact category. You just somehow have ask for a deflation on from a projective object, and projective objects also make sense. There are several equivalent definitions of what an exact object should be. So let's think about the condition of enough projectives for an exact category. What about generalizing it? Okay, for example, there's a theorem by Enomoto from 2017. Which tells you, okay, essentially small exact categories with enough projectives. We can describe them even in this generality, even without Hom finiteness or K-linearity, or this length category condition, even without thinking about this. They are the ones that are exact equivalent to resolving subcategories of what he calls this category mod C, where C is essentially a small additive category. He works very generally, so these are not only finitely presented functors, but yeah, somehow functors which have an infinite projective resolution, so to say. Okay, so that would be one starting point, and tells you a bit if you expect something like this to hold in the exact setup. If you want enough projectives, maybe you should think about resolving subcategories. That's a good starting point, I think. Okay, now more crucial point is the simples. And here's one example that appears, for example, in Enomoto's article, in another one of his articles. So if you take the path algebra of A3, now with the sinc orientation, then you get the module category is this. And now you have a resolving subcategory, which is the additive closure of these four objects, right? The simple are 2, simple projective are 2, the other 2 simple projectives, and this one injective. It's closed under extensions and closed under kernels of epimorphisms. Okay, now what are the simples of this category? And yeah, definitions of simples have recently appeared, and many people have been interested in some sort of the notion of simplicity and Jordan Holder series and so on, in these conditions. So for example, these two articles, and they say an object is simple if there's no non-trivial conflation building it, so to say. Okay, if you do this in this example, and this is actually taken from Enomoto's article, all the indecomposable, all these 4 indecomposables are simple with respect to this definition. However, if you take these 2 objects, L2 and I2, there's an obvious extension, right? So if you add L2 and I2, you get the sum of P1 and P3. So the sum of P1 and P3 is filtered by L2 and I2. So somehow you have 2 different composition series, right, of P1 plus P3. Yeah, and things are somehow not very nice. So in some sense, another perspective would be maybe P1 and P3 are not suitable. They're not really simple because they are in the additive closure of the filtration of L2 and I2. That's one other way to think about this. But then, yeah, you can also analyze sort of, if you, it makes sense to talk about the differential biquiver associated to this L2 and I2, and this also has some nasty properties. It's not what's called triangular, so it's also not so good. So there are certain subtleties that rise to this setup. So not all resolving subcategories are nice. Yeah. Recently, then, has also been defined a notion of a length exact category, and a category satisfying a Jordan-Holder property. So meaning just that somehow there's bound on the length of inflations, and also you have a Jordan-Holder property, all sort of composition series, so some sort of maximal inflation series, maximal filtrations have the same length and isomorphic composition factors. Okay. So this, I think, would be a nice place to look for more examples, look for further inspiration, what should be done. And luckily, in the case of quasi-hereditary algebra, this category of delta is one exact length category which satisfies the Jordan-Holder property. That has been known for a long time. And the symbols are precisely the delta I. Okay. And yeah, here's another theorem by Enomoto for the Jordan-Holder property for exact length categories and so on. So for example, you can look at the space of modules which are X orthogonal to some module of finite injective dimension. That satisfies the Jordan-Holder property if and only if the number of simples equal to the number of indecomposable projectives, which is also a nice property to have and quite natural. So maybe that's a good class of algebras to look at. Yeah? Maybe resolving subcategories of module categories of Artin algebras satisfying some sort of Jordan-Holder property. Okay. Here's another related article, a related result due to Keller, I think, unpublished, a proof of which you can find in our preprint. So if you have arbitrary modules and the category of filtered modules happens to be resolving, then actually you have a result which is similar to the case of simple modules, namely the positive part of the X algebra as an A-infinity algebra is generated by X1. So you might be tempted to ask for this algebra A, the subalgebra A, by just applying A-infinity cojoule duality to this positive part of the X algebra of the modules. But actually, there are examples where this does not yield a finite dimensional algebra. So there are also subtleties even in this setup where everything is nice and resolving. And there's also, I think here also there's some Jordan-Holder property holds even. So here's an example where things don't work out, just a Kronecker quiver. And the resolving subcategory given by the pre-projective component in one tube will yield some non-finite dimensional algebra A if you just take the infinity causal dual, because the infinity causal dual is just the path algebra given by the tensor algebra given by the dual of X1, because there's no X2 because you're in a hereditary situation. Okay, and let me finish the last slide with just a bunch of open problems that we're going to think about, right? Because my time is up, I think. Let me just shortly say they are of the type compute A-infinity structures on certain X algebras, right? Develop more tools for this ring extensions A and R, and then think about more this Jordan-Hölder property, maybe how it relates to infinity structures, and also this important question, when actually is the infinity casual dual of the positive part of the X algebra a finite dimensional algebra? Can this be described in other terms? Thank you. That's all I wanted to say in these lectures.
But let's thank Julian for his lecture and for his whole series of lectures. Thank you very much. Is there somebody in the Zoom meeting that have questions? The questions in the audience will be taken by Marco. Somebody in the Zoom meeting that would like to ask a question, please.
Excuse me, what do you have in mind by other nice cohomology theories?
Yeah, I'm not an expert on cohomology theories, but one could, I think for co-rings, for example, there are different cohomology theories, right? There's some analog of Hochschild cohomology for co-rings. There's something called Cartier homology and cohomology. So there are different things one could look at. We could also look at ordinary Hochschild cohomology with coefficients in R and so on. So there are different coefficients in V. Yeah? So just different cohomology theories, and maybe one of them is particularly nicely adapted to what we want to do here.
Thank you.
Well, any other questions from the Zoom meeting? If not, maybe we can see if there are questions in the audience. Marco? Sorry, is there any questions from the audience there? If not,
there are no questions.
Oh, okay, good. Well, then we thank Julian again for his lectures. And we resume after the coffee break.
Oh, thank you, and have a nice rest of the conference.